All right, we're going to look at a couple of examples of finding gradient vector and also directional derivatives. I'm going to skip the introduction part. I hope that everybody has read this portion of it, so we're going to go directly to the examples. All right, but just be sure at the last, during the, let me just make sure what we mean. Suppose you have a three-variable function, u is equal to f of x, y, z, and then if we let u to be a constant, then we get these so-called level curves. Okay, and the gradient has special meaning for these surfaces, called the level surfaces. Okay. And when we have curves, we also have gradients, and they also have very similar meanings over there. But for surfaces, this is especially the ones that we're looking at. Okay, so this surface over here, assuming that it's a level surface, so its equation is f of x, y, z is equal to some constant c. Okay, and then we have a point over here, and that's x naught, y naught, and z naught. Okay, and then we see this direction, the normal vector direction, is given precisely by these three derivatives, and we had this in the past. So the gradient factor. Okay. All right, so this is the fact we are actually using. Now let's look at an example. Okay. We want to find the equation of the tangent line and the normal line at a point on an ellipsoid. Now, we know what a tangent plane is. Tangent plane is over here, right? And this line passing this point in the direction of n is called the normal line. And we have this angle over here, 90 degrees. That's what's called normal. Okay. So remember, to find the equation of a plane or the equation of a line, we just need one direction and one point, right? So we just need to find the normal direction. Okay. And because we have an equation for the surface, it's more convenient if we just name this left-hand side to be a function. So we say, call this function fxyz. And that way it's easier to use our formula. Okay, if we do that, then x squared over 4 plus y squared plus z squared over 9 is equal to 3 is a level surface, right? Okay. And then we find the gradient vector. Okay. Find the gradient vector. Take the derivative, partial derivative, which is just x over 2, right? Derivative, this one is 2y. And this is pretty easy. And that's going to be 2 over 9z. Okay. Now plug in the point. Plugging the point is given -2, 1, and -3. So now we have the normal vector at that particular point. So we have this gradient vector is equal to, this is x over 2, so that's going to be -1. 2y, so it's going to be 2. And the last one, z is -3, so we have -6. Okay, and that is a direction vector for the plane, the normal vector. And we now have a point, so we can just directly write down. So the tangent plane equation is the following. We look at the vector -1 and then x plus 2, because it's x minus -2, right? And then second one we have 2 and then y minus 1. And last one here we have -6. Oh, y is -6. I think we should also have 9. Okay, yeah, because z is -3 and 2 over 9z is -6 over 9. All right, we recovered from this error. That's -2/3, and then z minus -3 is z plus 3, and it's equal to 0. All right, and from over here, what we have is -x minus 2 plus 2y minus 2 minus 2/3 z, again minus 2 is equal to 0. Okay, and then we have -x plus 2y and minus 2 over 3z, and minus 6 is equal to 0. If we don't like the denominator, we can say -3x plus 6y minus 2z minus 18 is equal to 0. And that is the tangent line's equation. How about the normal line? We can use the parametric form. So normal line passing the point, so we have x, y, z, and the point we have is -2, 1, and -3. How about the direction? Direction, the first one is -1, so it's -t plus 2t. And this one is -2/3 t. Okay, that's normal line's equation, and this is the tangent plane's equation. All right, it's pretty straightforward, and we're gonna pause over here, and then we're gonna start the second problem.